See my timer starting? All right. So I'm here to help you escape the the impending zombie apocalypse that's coming. I've got a little bit of experience as a zombie, and because of that experience, I think I've done pretty well in knowing how to be a good zombie and how to avoid becoming a zombie. And actually, I just have a dog that drives my car. But I'm a security architect at Polyverse Corporation in Bellevue, Washington, where we do cybersecurity through deception. So what is a zombie? I actually want to talk about software zombies. And software zombies, it's actually, what I want to get to is in the software world, it is incredibly easy for an attacker to build one small thing and find one hole and automate that and infect billions of devices across the world. Why is that? It's because all of software is built the same. If you download, or that attacker downloads Java version 1.5, and that attacker finds a hole in Java version 1.5, let's say it's running on 3 billion devices, they've now found a hole in over 3 billion devices. It's that simple, and that's why so many devices get infected. And so why is that if we have great security and great engineers? It's because those engineers don't talk to each other. Software still gets infected. And when they don't talk to each other, it looks like this. Simply, the security people say no to everything. And the engineers just say, you know what, let's just forget all the hurdles we have to go over. Let's go through them and knock them over and just get out there. And what typically tends to happen is the attackers get really happy about it, creepily happy. And that's not very good. So let's talk about terminology a little bit before we get a little deeper. So a vulnerability is a flaw in software. Typical flaw, it's a hole, whatever you can find. An exploit takes advantage of that hole, of that flaw. A 0 day, if you think about patient 0 in a zombie outbreak, that's what you're looking at with vulnerabilities. Patient 0 vulnerability. A patient 0 exploit takes advantage of that vulnerability. And then a virus or a worm automates all of the above. So the typical attack that we look at is not like you see in Hollywood. It's not like the Matrix. You're not typing and pressing one button and all the nukes go off. But typically what happens is they're time consuming, they're multi-stage, and they leverage a variety of attack vectors, which are ways to get into your machine. Now, first they fingerprint the system. They need to figure out what they're dealing with. After fingerprinting the system, they identify the vulnerabilities that might be in that system. Whether they buy them on the web for $100 or $100,000, they can still take that and put it and automate it into a virus, and it infects everything because all software is the same currently. And then they replicate the environment. And once they replicate the environment, they can test and test and test, just like Oceans 11 through 13. They just kept testing until they figured out how to get in, right? So that's exactly what happens in software. Now, I'm going to tell you, this right here allows you to get a root access, which is root access on a machine is admin access into a Linux system running Java. This little string right here. You put that in, and then you knock out and you have access to that system. You might think I'm crazy, right? Trump thinks I'm crazy. So let's unpack this a little bit. And so you have an 8-character minimum field, say, in your program. And you say, I'm going to take, maximum. You're going to take a maximum of 8 characters in this field. So what happens if you put in more than 8 characters? Well, there's a possibility the underlying system may be flawed. And so let's keep unpacking here. So 8 characters goes in, great. But if you look at the red right there, we put in 10 characters. And because the underlying system was flawed, they did not have a way to check and make sure we didn't overflow what they call the buffer. And so now we have 2 bytes of space where we can put an instruction. And typically attackers, what they'll do is say, you know what, I'll insert instructions that point to another memory location where I can upload 2 gigabytes that I can now execute on the system. And what that allows them to do is run privileged commands like create user. And if you have a Joe Smith on your network, and they can create J.Smith on your network, and now they have an admin user that they can go sell on the web for $10 to some script kiddie that can log into your system. And for the victim, I mean, you can just use your imagination. They run wild. You can set up a Bitcoin mining operation on there, right, which we've seen before. So again, this little string allowed full access on there. And 17-year-olds, like this person in here, me, build these in their basements. Now, the results of these attacks, obviously, are unauthorized access. People are, again, running Bitcoin mining operations, and it gets a little out of hand. So the impact is catastrophic. And so in the early 2000s, we saw $2 billion worth of lost productivity from the code red worm. The Sasser virus was $18 billion and affected critical infrastructure worldwide. Tons of viruses are out there every single day. So what's the solution? It's something that we call moving target defense. Being compliant and checking the boxes does not get you to be secure, and it does not create effectiveness. So what we do at Polyverse is we scramble all of your scrambled binaries. So we scramble every single program. That Java, the programmer that's trying to hack that version of Java has a 1 out of 8 quadrillion chance of actually finding out where we've moved and shifted the Java code around under the hood. And so we can get a lot deeper into that for all of you computer science folks in here. But at the very high level, we make it mathematically improbable to actually hack and build once and break everywhere, as everyone does today with viruses. So if you feel free, come talk to us. There's a guy in the blue shirt back there. His name's Archie. He's our CTO. And there's 2 more of us here to have a conversation. You want your attackers to look like this, just like the Seahawks at the Super Bowl. So that's all. Be a special snowflake like we are, and we're happy to talk more about it. So thank you. I don't know if I went over like by 12.3 seconds, but any questions here?
So I got a question about crypto locker viruses and cookie manufacturers. What are you guys seeing?
About what viruses?
The crypto locker.
Oh, the ransomwares?
Ransomware.
Yeah. So that exploited most of those. So 80% of the attacks out there are crafted memory attacks, just like the one I just showed you. That's 80% of them out there. And so what we do is those crafted memory attacks. I'll do a simple algebraic equation. If Java is what you're trying to build, let's say it's made up of 3 variables, A, B, and C. Let's say A plus B plus C equals Java, right? What we do is we twist all of those variables around under the hood, so it becomes C plus A plus B. It becomes B plus A plus C, all of that. So the attacker who's relying on that sequence of A, B, and C being in that sequence, it's no longer like that. And so imagine 8 quadrillion variables under there being shifted around. And so all of those that rely, the 80% of those is what we protect against 100% of the time. So.
Bring it a little bit closer to your question. If a person used our product on their desktop, that would protect them from ransomware. However, our current target is server architecture, so it wouldn't really mitigate for that style attack. However, the underlying concept of what we do could apply to every computer in the world and could mitigate all attacks that are memory.
Most ransomware is, gets that your vector is some secondary computer.
Right.
But then it's the actual server, some shares or whatever.
Yeah.
Right. Well, if you want to, we can have further conversation.
Yeah.
And there was a MongoDB one that also hit as well. That affected a lot. So.
When you talk to potential customers, what's their biggest question?
It depends on the customer, obviously, right? But their biggest question is, how does it affect my current pipeline? And actually, we are 1 line of configuration. And so it doesn't affect their pipeline at all, except for adding 1 line of configuration, which is becoming the primary repository in your Linux repositories. So what we do on our end is we scramble all the packages on our side, and you pull PHP, Apache, Node, just like you would in the past. So does that answer your question? Okay. All right. Both of you guys raise your hand at the same time. I don't know if you can fight it out, but I'll take I'll take you.
So the existing repositories, like there is a paper trail on them. How do we know that you don't get compromised?
We've got our architect, or one of our engineers. You want to take that, or?
Yeah. So we sign all of our packages just like everybody else, and you know that they at least were signed by us. If we were to be compromised, hacked just like anyone else, then we've got bigger problems at stake. Since I'm just a developer, I am not going to speak to the legal implications of what happened if we got hacked. However, we follow all the same security guidelines everyone else does, including the paper trail that you have from the public repos. You can go and look at the source of what we're compiling, and you can actually look and inspect our binaries as well. It's not like we do something secret and you can't then look at what it is you're downloading. You can look at what you've downloaded and inspect it just like every other piece of software to verify it is exactly what you want. Now, that means you have to do the same thing like you do with every other software. You have to audit it yourself. We're not doing that for you. You do by buying our product, you trust us inherently, and we keep that trust by not screwing you, right? Which we're here to keep you safe. That's their entire point. So I hope that answers your question, but if not, we can continue to talk further.
And one thing to add to that is the sizes, the hashes are going to be different because they're all different scrambles, but the sizes are going to be the exact same. Everything should act the exact same. And as far as if we get hacked, the other question is, another big question we get is what happens if, how do I know that your stuff is actually working, right? Just like any other binary out there, you're trusting that node actually works, right? And so the way that you do it is you test your application around it. If your application acts the same and does the same thing you expect, then there's your answer. So, one more question? Sure. Any other questions? Way in the back there. How do we get reproducible builds? We have a custom compiler on our server side, and so those builds actually we inject a large amount of entropy into the build process, into the actual compilation process, and so we have two very, very good compiler architects, one who wrote the book on compiler, one of the two books on compilers. And so injecting entropy into that process means that you can't really turn around and redo it. Like I said, 1 out of 8 quadrillion is a chance out of 2 compilations that you're going to get the same binary. And so we can run it 8 quadrillion times, I guess, but that's, by that point, something's going to be upgraded or updated. So you won't be able to get the same thing. So. Yeah, so some people have taken, so you're saying for testing processes and making sure that you're using it along the dev pipeline? Yeah, and so again, that goes back to testing, and your application is acting the way that it should act. If I download Node from node.js, whatever the website is, there's no guarantee that node is going to work and run. I mean, they have their bugs. All the same bugs that are there, all the same compliance issues that are there in Java or in the JVM stuff that we've built are still there when we go run it through the compliance checks that people run Java through. So, cool. Thank you, everyone.
Thank you, Kylie.